Okay, so let's take a look at just some examples. We're going to have a number. Remember hex, hexadecimal, base 16 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oops. Try that again. 13, 14, and 15. Where A represents 10, B represents 11, C represents 12, D represents 13, 14, and 15. If we wanted to go from DAC and base 16 to our decimal, base 10, then you put 3 blanks, DAC like that. This first one will be 16 to the 0 power, 16 to the first, and 16 squared. And D from over here is 13, A is 10, and C is 12. So our conversion here, what we do is we take 13, the number up here, times the number down here. So we got 13 times 16 squared plus 10 times 16 plus 12 times, and anything to the 0 power, remember, is equal to 1. And I'll be right back. I didn't bring my calculator. So we got 16 squared times 13 plus 160 plus 12 gives us 3,500. And that would be our answer. They have a mixture in the book. In the book, they do not limit themselves to base 2, the binary we looked at. They do not limit themselves to octal, base 8, or base 16. So the hex. One case they had base 5. Another example I think I saw somewhere was base 9. So this same principle holds true. If this was base 5, and I mentioned this last time, instead of 16 to the 0, it'd be 5 to the 0, 5 to the first, 5 squared, on up. Is there any questions on that one? Okay, let me do a new. And let's look at an example of base 5. So what digits can I use for base 5? 0, 1, 2, 3, and 4. Remember, it's always one less. So base 5, you can use up to 4. Okay, so let's look at 1, 2, 4, point. 1, 3. This is base 5.
Base 5?
Base 5, yes.
Does it have a name, like octodecimal?
I don't know. The book never gave me a name for it. They just said base 5.
Okay.
I'm sure it does have a name. And we want to change that to decimal. Well, same principle holds true before. If I put 124.13 here, this is 5 to the 0. It always starts off with the 0 power. This is 5 to the first. This is 5 squared. Do you remember what this is?
-1.
-1. And this will be 5 to the -2. So this one's 25. This one's 5. This one's 1. And this would be 1/5. And this would be 1 over 25. And then, same principle, we're going to take the number here times the number in the bottom here. So this first one, we got 1 times 25 plus 2 times 5 plus 4 times 1 plus 1 times 1/5 plus 3 times 1 over 25. 1 times 25 is 25 plus 10 plus 4 plus 1/5 plus 3/25. So we got 35, 39, and 1/5 plus 3/25 gives us 0.32. So this is the same number in decimal. If you had different bases that you're working with, base 16, same principle. You'd have 16 to the 0, 16 to the first, 16 squared. Over on the right side, you'd have 16 to the -1, 16 to the -2. Now, the book talks about some specific problems, and I want to refer to those. They want you to go like from hex to binary directly. That's what the instructions specifically say. Whenever they say to do that, I do not want you to do that unless you want to research it on your own. We don't have time to cover all that. In our case, you would take it from hex and you'd take it to decimal, and then you would take it to binary. So you do that kind of conversion. So that's just generally on the problems I'll assign out of the book. I don't think we'll get through the chapter today. We'll probably get through it, finish up chapter on Monday, and get in chapter 2 then. Which means I'll probably have a test out there that you can take online probably by the end of next week. So it'll be the first test. Okay. Now let's just refresh the memory going the other way, going from decimal to another base. Everybody got that written down? Okay. Okay, so if we're going to start out with 132, and this is going to be in base 10, and we want to change that over to hex, base 16. We got 16 to the 0, which is 1, 16 to the first, which is 16, 16 squared, which I believe is 256. Not that we need it. We don't even need 256. But 16 to the third is 4,096. So we're starting with 132. We look for the first number that, and we're going from the left. So we're looking for the largest number that's less than or equal to 132. So starting out, that would be 16. So we take 132 divided by 16. That gives us 8. And 8 times 16, 128. If you subtract those, you get 4. So we're going to have two blanks because this is the one we started with. So the number we put up on top here, the 8, goes in our first blank, goes above the 16 that we just divided by. Now our remainder is our new number we work with. And so going down here, we're looking for the next number that's less than or equal to that, which is 1. 1 goes into that 4 times. 4 times 1 is 4. Subtract that. And 4 is the next number that goes here. So 132 base 10 is going to equal to 84 in base 16. One more refresher, and then we'll take a look at the new material. But is there any questions so far, Nat? Okay, we got 201.12. And I don't think we looked at a changing that to hex when you had decimals. The example we looked at in the book, and let me grab. Example we looked at was octal on page 9. Fairly simple. Remember the whole part, you convert like normal. So let's take a look at 201. Got 16 to the 0, which is 1. This is 16. This is 256. 16 to the 0, 16 to the first, 16 squared. We look for the first number that's the largest number that's less than or equal to 201, which would be 16. And so then we do our old style division. It goes in there 1 times 16, 4, 41. Doesn't go into 3, does it? It's 2. 32, and we get 9. So we're going to put 12 in this blank. Remember what 12 is? C, because A was equal to 10, B was equal to 11, C was equal to 12. Now 9 is our new number we're working with. And so we're going to divide it by the next number, which is 1. 1 goes into that 9 times with a remainder of 0. So that means there's a 9 in here. Which means that this is going to be 201.2 base 10 equals C9 point something. Okay, now our decimal portion. We take our decimal, which is 0.12, and looking at the example on page 9, what do you think I'm going to multiply that by? By 16, yeah. You always multiply by whatever base. So if they gave you something base 5, you'd multiply by 5. So we got 0.12 times 16. We get 1.92. The 1 goes up here. It's our first decimal place. And the 0.92 you carry down here. And then you continue the process. So you can multiply that by 16. Which is 14.72. Which means 14 goes up here. What's 14? E. And the 0.72 goes down here. And you continue the process. You multiply by 16. Gives us 11.52. We already said 11's B. And then 0.52 carries down here. Doesn't look like it's going to end. So we've got 8. You carry the 0.32 down here. I'll stop after this one. Otherwise, I could continue the rest of my life probably and still not have it ever end. So I got 5.12, and I'll put a 5 here. And then I'll put ... to indicate it keeps going on forever. And that would be our answer. Everybody good on that part? Okay. Well, let's refresh our memory on addition and subtraction. A big part of what we're going to focus on today is addition and subtraction. We got 1, 0, 1, 1, 0, 1. And we want to add 0, 1, 1, 1, 0, 1. These are both base 2. Now, the book focuses almost exclusively, when they get into items like this, on binary. You don't see much of a mixture. Now, 1 plus 1 is what? 2? We can't use 2, though, so what do we put here? It's what? 0. And what do we put here? 1. Because we're bringing over a base in terms of 2, so we bring over one of them. How about if we had a different base? Like base 8. If I had a 17, I'd come up with when I added it.
Still make it 0. Would we carry 8?
Let me think of this. I believe you carry a 2 over. I'd have to play with it and see. I haven't done a octal or hex in a long time. Because when we have like 15 here, 19, what's that? Okay, 18. You're adding these together. We're bringing 9 plus 8 is 17, 19, 24, right? We're putting a 4 here, and we just don't even think about it. What do we put here? 2. Now, it was 24, wasn't it? And we left 4 down here, which then meant we had 20. So, and when you think about it, if you put a 2 here, there's like a 0 here, isn't there? Okay, so base, okay, we're bringing over 16. This is 16 to the 0, 16 to the, or no, octal is what I meant. 8 to the 0, 8 to the first. So when we bring that over, I think we want a 2 there, don't we? Does that make sense? Yeah. This is like 2 sets of 10s, isn't it? And in our case, if we had 2 sets of 8s, we bring a 2 over. Always throws me. I can get them, but I struggle with them because I really have to think about what does that represent. Now, that's why they almost exclusively focus on the binary, is because they want to introduce a concept, but they don't want to sit there and hurt your brain at first. Okay, 1 plus 0 is 1. 1 plus 1 is what? 2. So we put a 0 and carry over a 1. Because we're bringing over one set of 2, right? So 1 plus 1 plus 1 is 3. We're going to leave a 1 here and bring a 1. Because we bring over one set of a 2. And then 1 plus 1 is 2. So we put what? 0. And carry over this. 1 plus 1 is 2. So we put a 0 and carry over a 1. And that would be our answer. Now subtraction. One, 1, 1, 0, 1, 0. Then we're subtracting 0, 0, 1, 1, 1, 1. This is following along in the book. The example's on page, kind of bounces back. The example's on page 6. Well, we're going to need to borrow one and then see what happens. Can I subtract 1 from 0? No. So I need to borrow 1 from here. So this goes to 0. What does this become? Oh, it does.
2. Yeah. 2?
Yeah, remember when we, if you look at the example on, in the middle there, when we borrow 1, like you say, we're bringing 1 over, but we're bringing specifically what? One set of 2.
Binary.
Yeah, binary. They don't really show it there. Okay, so let me see. This would be a 2. 2 minus 1 is 1. Can't borrow or can't do this here, so I come over here. Can't borrow from there, so I come from here. This goes to what? 0. Now this next place over, what does this become? 2. But really what we need is right here, so we need to borrow 1. So that goes to 1, and then this goes to what?
2.
So 2 minus 1 is 1. 1 minus 1 is 0. 0 minus 1 I can't do, so I come over here and borrow. And then this becomes a 2. 2 minus 1 is 1. 0 minus 0 is 0. 1 minus 0 is 1. And that would be our answer. Now we brought a 2 over. Not that they got any in there that I know of, but if you had octal and you're borrowing 1, What would you bring over?
8.
8, exactly. You have to keep in mind when we're working with this, you're not just like bringing just a single digit over again like decimal, which isn't a single digit. It represents a set of something. But we're bringing over a set of 2, set of 8, a set of 5, whatever. Okay. Enough about that. Let's go into new material. This is on page 11. Let me get my book.
I have a question.
Sure.
So if you want to go from hex to octal, let's say, you will always have to go through decimal first, right?
I would. I think it's easier.
Okay.
Okay. This is what is this? Am I on the right page? Doesn't look like it. Let me go back one. Here it is. E-book looks a little bit different than the regular book. This is talking about binary numbers are difficult to work with because they require 3 or 4 times as many digits as their decimal equivalents. For example, a binary number, however many ones is there, is equivalent to the decimal 4095. However, digital computers use binary representation of numbers, and is sometimes necessary for the human operator or user to communicate directly with the machine by means of such numbers. So, sometimes necessary. That does not mean you're going to spend every day sitting there doing a conversion from binary to decimal or vice versa. Depends, I suppose, depends on what kind of programming you do. In 13 years of programming, I never did that once. But if you're designing something at the electrical, the lower level, or you're doing electrical engineering, it could be you have to do that more often. Let's see. It says one scheme that retains a binary system in the computer but reduces the number of digits a human must consider utilizes the relationship between the binary and the octal or hex. And talks about the conversion during communication. Okay, most important down here. It does that. Most computer manuals use either octal or hex decimals to specify instructions and other binary quantities. The choice between them doesn't really matter because hex is superior because it can represent a byte with 2 digits. Again, your goal is conservation of space. And that's why, remember how I said before you can represent a very large number with less digits? So that's what it's referring to. Now this next part gets into complements of numbers. And they explain why this is important for digital computers. Complements are used in digital computers to simplify the subtraction operation and for logical manipulation, which we'll talk about later on. Simplifying operations leads to simpler, less expensive circuits to implement the operations. There are 2 types of complements for each base R system, the radix complement and the diminished radix complement. The first is referred to as R's complement, and the second is referred to as R-1's complement. When the value of the base R is substituted in the name, the 2 types are referred to as a 2's complement and 1's complement for binary representation, and a 10's complement and 9's complement for decimal numbers. Well, let's see what in the world that means. Find an example here. I'm going to work the one they give. For decimal numbers, R is equal to 10. So in this case, you got this. Okay. You got the book in front of you in theory, so I'm going to show this over here. Now, it's much easier than what I'm showing you. I'm just showing you the theory behind it now with an actual example. On the book, I'm on page 12, and they tell us, let's see, for decimal numbers, R is equal to 10. And then R minus 1 is equal to 9. So we plug 10 in here, you get 10 minus 1, or 9. And the formula they give us is specifically R to the n minus 1. We'll talk about the big N here in a minute. So if I had R, which is base 10, so that's 10, and the example they give, n is 4. They don't really say what n is, do they? But n is how many digits you have in your number. So they don't specify that, but that's like if I had 4 digits. So I'm surprised they don't actually say that. And then minus 1. So we're going to have 10 to the 4th. So we're going to have 4 zeros minus 1, which gives us 9,999. So that's this part of the formula here. Now specifically, the entire formula is R to the n minus 1 minus big N. Now, if our base is 10, this doesn't apply across the board. Obviously, if your base is different, then it won't be this way. But if your base is 10 and number of digits is 4, what does that imply you're going to have? 4 nines. So it's you don't have to sit there and plug it into that formula. It's pretty straightforward. The example they give you, they want you to find the nines complement of 546,700. So we got 546,700. And we want to find the nines complement of this. Now, I might look at that and say, well, is that base 10? Remember the formula that they referred to up above is they said this is specifically focused around R minus 1's complement. So using this diminished radix complement, if I say I'm wanting to find 9's complement, what does that mean the base is equal to? 10. It's 1 greater. Because going backwards, imagine if you put 10 in for this little r. 10 minus 1 is 9. 9's complement. How about if it said 8's complement? What would your base be? 9. because it's always one greater, because you're really subtracting 1 with this form. Okay, so this is base 10. When we say 9's complement, we're talking about base 10. And how many 9's am I going to have? 6, because I actually got 6 digits. That's what our little n is. Now that's this part right here. That's this r to the little n power minus 1. Minus, and then your actual number. That's what the uppercase n stands for. Assuming I could write it down correctly. Let's try it again. So 546,700. And there's my calculator, but book already has subtracted them. So that gives us 453,299. Notice the next example. I thought this was interesting. Is there any questions on that example? Our next example, it wants us to find a 9's complement of 0, 1, 2, 3, 9, 8. How many digits do I have? 6. They're specifically putting a 0 here, aren't they? When you're talking about designing like a circuit or memory or whatever, you're going to find that you're going to have so many digits. Even if the first ones are zeros, you still have so many digits. So it still follows that same pattern. So we're going to have 6 9's, and we're going to subtract that number, which then gives us 987,601. Good on that one? Okay. That's how you find the 9's complement, specifically focused on the diminished radix. Now, you start looking in the book at the examples, and they're going to focus on certain complements. They won't focus on all of them, but there's certain ones they focus on. I think the only one that I see a little bit different is they got a 16's complement here. And in that case, if you got 16's complement, this then changes, doesn't it? So this is where you'd have to then modify this. Your base is what, 16? And then you'd have your however many digits, that's what little n represents, and then minus 1. It also depends upon whether it's diminished or it's just the normal one. Let me go ahead and clear that off, and then we'll look at the next example.
Are these from the book?
These are from the book. This is on page 12 still. It wants us to find a 1's complement of 1, 0, 1, 1, 0, 0, 0. Now, you could use the same formula, and they actually go through and they show the formula derived and so forth. Or not derived, but they show how to use the formula on an actual example. But then they put in bold. It says, therefore, the 1's complement of a binary number is formed by changing 1's to 0's and 0's to 1's. So does it get any easier than that? The ones complement of this would be 0, 1, 0. So the ones become zeros, the zeros become ones. And then 0, and then 1, 1, 1. And that's our answer. That's a ones complement. Let me show one more. What's this one have? 0, 1, 0, 1, 1, 0, 1. So again, you just flip them. So that first 0 becomes a 1, then 0, 1, 0, 0, 1, 0. Assuming I flipped them all correctly. And that'd be your answer. Is there any questions on the ones complement?
Can we do it manually? Just to see how it works.
I'll do a small number. And let's see. They give the example of this work on 10,000. Okay, so if we got our n is equal to 4, our formula is r to the n minus 1 minus big N. So if n is equal to 4 and our base is 2, we're going to have 2 to the 4th minus 1 minus big N. 2 to the 4th is 16 minus 1 minus big N. This would be 15 minus big N. But 15 is in decimal, isn't it? So that's base 10. If I think about what the binary version of that would be, this is 2 to the 0, so that's 1. 2 to the first, 2, 4, 8. The next one would be 16, wouldn't it? So if I change this to binary, two, 3, 4. Does 8 go into 15? Yeah. So there'd be a 1 there. Now 15 minus 8 is 7. Does 4 go into 7? Yeah. So there'd be a 1 here. 7 minus 4 is 3. Does 2 go into 3? Yeah. 3 minus 2 is 1. Does 1 go into 1? Yeah. So that'd be all 1s. Minus then our number. Does that make sense on the number we come up with?
I got that part, but what I was confused about was the rule that you flip the binary stuff over.
Oh, let's see what you're saying. If you let's see if they already give you one. Well, let me continue this example then. If, let's say, n is equal to 1, 0, 1, 0. Now, if I do my subtraction like normal, 1 minus 0 is what? 1. We flipped the digit, didn't we? What's 1 minus 1? 0. We flipped the digit. 1 minus 0, 1. We flip the digit. And 1 minus 1 is 0. So we flip the digit. It just always works when you're talking about binary like that, and you're subtracting it from all ones. It'll always just flip all the digits.
And how do you find n? Capital N.
Oh, that'll be given.
Okay.
Yeah, this is what the problem will actually say. So it'll say find the ones complement of this. Questions on the ones complement? Okay. Now, next thing on page 12. Well, I shouldn't say 12. Yeah, it is 12 in your book. Let me look at the ebook, see where it's at. That was the diminished radix complement. This is the radix complement. The r's complement of an n-digit number, uppercase N, and base R is defined as R sub little n minus big N, where n is not equal to 0. So this formula is different, isn't it? It's not the same principle as the other one. The other one was it was R to the n minus 1. So this doesn't have the minus 1. You can think of the minus 1 as diminished, so it reduces it. And they talk about, you can sit there and read that. I'm not going to sit there and read it to you. It's a fairly simple idea. And I actually summarized it on a piece of paper so I can type it up for you. Because at first, when you read that, it's just like, well, this doesn't seem to make much sense. Now we're going to have the tens complement here. And it talks about can be formed also by leaving all least significant zeros unchanged, subtracting the first non-zero least significant from 10, and subtracting all the higher significant digits from 9. What in the world does that mean? Okay, so the tens complement, what you're going to do is from the left, you're going to leave from the left. I must have been pretty tired when I typed that up last night. That when I said that, wait a minute, that doesn't sound right. From the right. From the right side, you leave zeros alone until you reach the first non-zero. So then you leave zeros alone until you reach your first non-zero. Subtract this digit, the first non-zero, from step 1, from 10. Then subtract all the rest of the digits from 9. And while you're writing that down, I'm going to go. I'll be right back. We've got a break. Talk for 2 hours before it starts going. Now, if you're wondering where we're headed with this, subtraction, when you're talking about a digital device, is inefficient. So we rewrite it as addition so we can efficiently, through the machine, do the calculation. You're going to see us do the simplest problem that you could easily do in your head. You're going to see us kind of do it what seems like a hard way, just because we're looking at the efficient way for a machine to do it. Is anybody still writing that down? Okay. Now the example we're going to look at is on, let's see, what page is it on your book? It's on page number 12. And it's kind of down at the very bottom, says the tens complement of 0, 1, 2, 3, 9, 8. Okay, so let's go write that down. We got 0, 1, 2, 3, 9, 8. And specifically what we're finding is find the tens complement. Let's look at our steps. From the right side, you leave zeros alone. Those are what they refer to as the least significant. It says so 0 is in the least significant position. Least significant position are your smallest values, right? Which is on the right side. Okay. Do we have any zeros on the right side? No, we don't, do we? Then it says, so our starting digit is this right here, since there are no zeros. So that's our starting one. It says to subtract this digit, the first non-zero, from step 1 from 10. 10 minus 8 is 2. And then it says all the rest, subtract all the rest of the digits from 9. So 9 minus 9 is 0, 9 minus 3 is 6, 9 minus 2 is 7, 9 minus 1 is 8, and 9 minus 0 gives us 9. That's where they come up with the 987,602. And that's your answer. Clear as mud? Let's take a look at another example. I'll make up one. This isn't really hideous in the calculation, so I don't need to do a problem to actually check my answer. Okay, let's say I got 7, 1, 2, 3, 0, 0, 0. And our goal, again, is to find the tens complement. Now, you notice on this previous example, this leading 0, what would you normally do on that just in basic math class? You just drop it, right? You can't do that here. If you drop it, then you're going to come up with one less digit here. So you won't get the right result. Because remember, our eventual goal is to design the circuits, memory. You think of all those. They're in groups, aren't they? Groups of 4, groups of 8, whatever you're designing. Well, really, it's based on powers of 2, but okay. So find the tens complement. If I go to my steps, it says from the right side, leave zeros alone until you reach the first non-zero. So 0, 0, 0, we leave those alone. They just stay as is. Here's our first non-zero. And I say subtract this digit from first non-zero from step 1 from 10. So 10 minus 3 gives us 7. And then you subtract each one of these from 9. 9 minus 2 is 7. 9 minus 1 is 8. 9 minus 7 is 2. And that would be our answer. Okay so far? Now that's 2 examples down at the bottom of page 12. Let's talk about the nines complement. And again, I got this written down to help you. Oops. And help myself. Nines complement. First thing we're going to do is from the left. From the right side, we're going to leave zeros alone until first non-zero. Step 2, we're going to subtract this digit, the first non-zero, from step 1 from 9. Step 3, we're going to subtract all the rest of the digits from 8. Now this is very specific. This is not diminished. This is the radix complement. So that's what these two apply to. We'll probably make up an example, but do you think you could, based upon this, write the steps yourself for finding 16's complement? Well, let's see. Look at step 1 here versus step 1 down here. Until you reach. Let's try that again. Reach first non-zero. What does step 1 and step 1 look like? Exact same thing, doesn't it? Yeah, exact same thing. So 16's complement would say the exact same thing. It would say from the right side, leave zeros alone to reach your first non-zero. Then that digit you just found, notice step 2 here and step 2 here. Subtract this digit, first non-zero from step 1 from 10, and then one says from 9. So 16's complement, what would you subtract it from? 16. Now if you look at step 3 and step 3 here, subtract all the rest of the digits from 9 from 8. So for 16's complement, what would you subtract it from? 15. Yeah, so I think there is one problem at the end of this chapter where they're asking you to work with 16's complement, and there's nothing exciting about it. That's the exact same principle. Let's look at a couple of examples for the 9's complement and see how that works. Actually, I could probably make it up. Okay. Okay, so we got... What if I just stop the recording? Let me just double check that real quick. There we go. Okay, example, we got, let's see, 0, 1, 2, 3, 5. And let me see, we're working on, what did I say? 9's complement. Step 1, you ignore all the zeros. The zeros from the right side just carry down. You ignore them. So we don't have any zeros from the right side, do we? For our first non-zero digit is this one right here. Our instructions say to subtract that from 9. So 9 minus 5 is 4. And then the rest of these are subtract from what? 8. So 8 minus 3 is 5. 8 minus 2 is 6. 8 minus 1 is 7. 8 minus 0 is 8. So our 9's complement is this right here. Then work one more. Okay, let's see. 2, 0, 5, 0, 0. And again, I'm wanting to find the 9's complement. Okay. What do I do here? Just bring the zeros down. Coming from the right side, the least significant, you just bring them down. You don't do anything with them. That's 4. We subtract that from 9. What do I subtract these from? 8. So 8 minus 0 is 8. 8 minus 2 is 6. So this would be our 9's complement. I won't actually type out the 16's complement. I think you see the pattern there. But let's take a look at 2's complement. Two's complement. Okay, so step 1, from the right side, leave zeros alone until you reach the first non-zero digit. At that point, you're going to leave the 1 alone. Then flip the rest. 1s become 0s, and 0s become 1s. And we're going to look at a couple examples of that.
So the first one from the right stays the same?
Exactly. I'm not sure why the book puts this. This is actually no different than the other two we just typed up there. It's no different than the base 16 example we gave. I could write it in the same words. And I'll actually talk about that after we work at using these steps. Is everybody still writing that down?
What does step 2 mean?
The digit you run across, it's a 1, you leave it alone. You don't. It just stays as is.
The first one from the right side.
Oh, until you reach first. This right here?
Leave 1 alone.
Oh, that means just leave the digit 1 alone.
Aren't you supposed to flip them?
Sort of. I'll show that with an example. Okay, so let's do a file new. And the one we're looking at in the book we got 11011100. And we want to find the 2's complement. Okay, so we're going to look at this 2 different ways. Our first step says from the right side, leave 0s alone until you reach your first non-zero digit. So this 0 remains as, this 0 remains as is. So our first non-zero digit is this 1 right here, right? Now that's what this is saying. Leave the digit 1 alone. So this 1 you see right here just carries straight down. And then all the rest of these, they flip. 1s become 0s, 0s become 1s. So this 1 here becomes a 0. This 0 becomes a 1, this 1 becomes a 0, and this 1 becomes a 0. And that'd be my answer. So again, 0s from the right side remain as is. The first non-zero digit stays as is, and then you flip these to the opposite. Well, I said that basically it's the same as this. Let's take this and modify this. Just to show you there's nothing new we're doing. So 2's complement. From the right side, leave 0s alone until you reach first non-zero. Subtract this digit from 2. And then subtract all the rest of the digits from 1. So that would be our modification for those steps, wouldn't it? This is what we've been doing for the 9's complement and 10's complement. Okay, so let's follow that. Do this example again. 1, 1, 0, 1, 1, 0, 0. From the right side, leave zeros alone to reach first non-zero. So that 0, 0 carries down. Here's our first non-zero. You subtract that from 2. Well, 2 minus 1 is 1. And then you're going to subtract all the rest of these from 1. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 0. It is exactly the same steps. That's just a little shortcut that the book gives you on how to do that. Does that make sense?
Yeah.
Okay. We'll take a look at one more and then we'll... I'm sorry, go ahead.
Can I ask a question about something previous?
Sure.
Could you go back to the page where you first introduced the formula r to the power n minus 1 minus n?
Right. What about it?
Could you go back to the page?
Oh, go back to the page. Okay. Which one do we want to see, the diminished or the radix?
There was an example that you worked on. 9's complement at 0, 1, 2, 3, 9, 8. We just had 9 digits, 6 digits of 9 minus the number. Could you explain how that works?
Oh, this right here. Since we got 6 digits, then your formula is you got r to the n minus 1. And so r is your base 10. And so then you got 6 digits, so you got 10 to the 6 minus 1, which gives you 6 nines.
Okay.
And it always works that way.
So whenever you give us a number n, we just subtract it by the base. And if you don't, we use the other formula, other rules.
Those other rules, yes. Yeah, the diminished is where you, so like if you're working with the 9's complement, that's where you subtract them from all 9's.
Mm.
Now, do not think that if it's the 8's complement that we're going to subtract it from all 8's. You have to plug it into the formula because you'd have 8 to, like if we had 6 digits, you'd have 8 to the 6th power minus 1. And I'm pretty sure that's not all 8's. Let me check. Eight to the 6 minus 1. No, it's not all 8's. So it's you have to actually use the formula. This is a very specific instance when we're talking about base 10 where it works out really nice like this. Though to be honest, I don't think I saw any diminished radix that was a different base than what you see here. There's the reference to this chapter actually is there's a whole book on this stuff. So if you're really into mathematical operations on different bases, I mean, you could study it for 16 weeks, just that concept. Okay. Let's see. Oh yeah, I was going to show another example of the 2's complement. So I'll work even I can make one up pretty easy. Let me just make one up. There's really nothing to check. These are pretty straightforward. Let's see. I got 1, 0, 1, 1, 1, 0, 0, 0. And I want to find the 2's complement. I'm sure I'm spelling that wrong over and over, but oh well. The easier formula, it's one for the book kind of outlines, this right here. says from the right side, leave zeros alone until you reach your first non-zero digit. So these 3 zeros remain as is. Then it says leave the digit 1 alone. That we're sitting right here. This is our first non-zero digit. So you leave that 1 alone. And then you flip the rest. 1s become zeros, zeros become 1s. So we got 0, 0, 1, 0. And that'll be our answer. Is there any questions on 2's complement? Now we're going to take a look at this to figure out how to do subtraction. And that starts on page 14. We already reviewed just how to do normal subtraction anyway with binary and so forth. So this is going to go a little bit further. This is on page 14, example 1.5. So let me clear this off. And we're subtracting 72,532 minus 3250. From a human standpoint, we can do this pretty easy. That's not the goal here. The goal here is we're going to figure out how we can use the digital to do it digitally. If we just did it normally, 2 minus 0 is 2. Can't subtract 5 from 3, so I have to borrow 1. So this goes to 4. Then I got 13 minus 5, and tell me if I screw up on this, my basic math. 4 minus 2 is 2. 72 minus 3 is 69. That would be our answer. So 72,532 minus 3250. Now the steps for this are at the top of page 14. Most important is being able to identify them properly. We got M and N. So this is M, and this represents N. Now this says to be done as follows: add the minuend M to the R's complement of the subtrahend N, assuming I'm saying that right. Mathematically is equal to that. What that's saying, and you can see it, they tell you, we want to leave M as is. So that's 72,532. And then we want to find the tens complement of N. Now remember your tens complement. These are your steps we just looked at. Coming from the right side, you ignore zeros. We don't have any zeros, do we? Our first non-zero digit, oh wait a minute, I'm looking at the wrong page. Here's the N over here, isn't it? We do have a 0, don't we? So that 0 carries down. Our first non-zero is right here. What are we going to do to that?
10 minus 5.
10 minus 5. So that's going to give us 5. And then we're going to subtract the rest of the digits from what? 9. Now, How many digits do we have on our number up here?
4.
Or our first number, M. We got 5 digits, don't we? How many digits do we have down here?
4.
4. We're missing one, aren't we? So what should go here?
0.
0. Okay, so now if we subtract these from 9, 9 minus 2 is 7. 9 minus 3 is 6. 9 minus 0 is 9. And this is now changed to addition. Now we add this just like normal. 2 plus 0 is 2. 3 plus 5 is 8. 5 plus 7 is 12. Put the 2. Carry the 1. 6, 7, 8, 9. And then we got 16. We're going to go back to the steps here in a minute. But we got subtraction. And we said we have 5 digits here. How many digits did we end up with? 6. We can't have 6 digits if you're subtracting. You have 5 as your most digits. So the book tells us to do a minus minus 100,000. And so then that's going to give us 69,282. And that's our answer. Now I subtracted this, and you might say, well, your original goal you said is that we don't have to do subtraction. And you just threw another subtraction. Or in addition, you did an addition also. But what does that equate to when you subtract that 100,000? Just dropping that first digit, right? So it's not really subtraction when you're just dropping that digit. You're just ignoring it. Is there any questions on that? Okay, where in the world does that come from? You get down to here. It's talking about if m is greater than or equal to n, or if m is less than n. It talks about the n carry. And it says if m is greater than or equal to n, the sum will produce an n carry, r to the n power, which can be discarded. What is left is the result m minus n. N carry of r to the n. R is our base, isn't it? N is how many digits we have. Well, how many digits did we have initially? Our base is 10. We had initially 5 digits, didn't we?
Yes.
So that's 10 to the 5, which is equal to 1 and 5 zeros, which is this right here, 1 and 5 zeros. So when your m is greater than your n, you're subtracting this at the end like that. According to our algorithm. Now I'm going to show another example lab, but is there any questions on that one?
Copy it.
The what?
I just need to copy the thing.
Oh, okay. Yeah, go ahead. I'm going to make up one so you see one different than what's in the book. Now, it's pretty easy to see if you did these right or not. Because if you do normal subtraction, you see how we come up with the same answer is by doing it this method. So if you don't come up with the same answer, that means you did a basic math error somewhere.
So what did you ask us?
We're-
What was the problem?
Basically, we're wanting to subtract without using subtraction. So that's the idea behind this.
Okay.
So the actual instructions out of the book say using 10's complement, subtract the two numbers.
Yeah.
Okay, so let me clear this off. You got it written down?
Yeah.
Okay. And let's say we have 23,560 minus 9,100. Wait a minute, my eyes are getting off. 2, 3. Okay, so we want to subtract those. Let's just do it by the normal means. We have to borrow 1, so that goes to 5. This 10 minus 3 is 7. 5 minus 2 is 3. 5 minus 1 is 4. 23 minus 9 is 14. So that should be our answer when we're done. 23,560. And we got how many digits? 5, which means we need 5 digits here. So we're going to put a leading 0 there. 9, 1, 2, 3. This is our M. This is our N. Now your M remains as is. So 23,560. We're changing it to plus. Now coming from the right side, do I have any zeros? No. So this is our first non-zero digit. What am I going to, and this is using, I should say, using 10's complement. What am I going to subtract that from? 10. So 10 minus 3 is 7. What am I going to subtract the rest digits from? 9. So I got 9 minus 2 is 7. 9 minus 1 is 8. 9 minus 9 is 0. 9 minus 0 is 9. Now we're going to add these together. 0 plus 7 is 7. 6 plus 7 is 13. Put the 3, carry the 1. That's 14. So carry the 4, or put 4, carry the 1. Gives me 4, and that gives me... Yeah. Now remember, this, since M is greater than N, our algorithm says we need to drop this first digit. Basically, you're subtracting R to the little n power. So our answer is going to be the 14437, which is what we came up with doing it the normal way. But in this case, we had to do zero subtractions. We just had to drop that first digit. Questions on that? Well, let's take a look at subtracting using the 2's complement. That's the example on page 15. So I'm going to clear this off. Is anybody still writing it down? Okay. And let me actually use their example. We got 1, 0, 1, 0, 1, 0, 0. This is binary. Minus 0, 1, 4 ones, 0, 1. And we're going to use 2's complement to do this. this is our M and this is our N. For the 2's complement, remember your M stays as is. You never affecting that. 101, 01, 00. We're changing this to addition. And 2's complement. We're going to ignore the zeros coming from the right side. There are none, are they? I said the 1 stays as is.
And we flip the rest.
And you flip the rest. I think I screwed up. I didn't write it down out of the book right. Let's try it again. Sorry. I wrote down the 2's complement directly. I wanted it to match the book so you could see it. The original problem is up above. So it's 1, 0, 1, 0, 1, 0, 0. Minus, I was looking at that, I was thinking, well, the book's doing it wrong. There we go. That's the initial problem. Okay, so this is our M, this is our N. M stays as is, 101, 01, 00. Coming from the right side, there are no zeros for N, the least significant digit. So we're right here. That 1 stays as is, and like you point out, everything else flips. So this becomes a...
Are we missing a 0 in the middle?
Do I have one less? 1, 2, 3, there's 4. One zero one zero one zero zero. Yeah, I got this skewed. Okay, try number 3. Hardest problem is actually writing the problem down correctly. Okay. Sorry about that. Let's see, 1 1. Then there's 1 2 3 4 zeros. 1 2 3 4, and then a 1. Okay. So this is M. This is N. M stays as is. So we got 1 0 1 0 1 0 0. Changing this to addition. Our first non-digit, our first digit that's not 0 is this one right here. So that stays a 1, and you flip the rest. So 0. We got 4 zeros, so we'll have 4 1s. And then that becomes a 0. That's where they come up with that first line in part A. They come up with the 2's complement. And that's the 2's complement of N. Now we're going to add. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is what? 2. So I put the 0 and I carry the 1. 1 plus 1 is 2. So I put the 0. I carry the 1. 1 plus 1 plus 1 is 3. So what do I put? 1 and carry the 1. 1 plus 1 is 2. So I put what? 0 and carry the 1. 1 plus 1 is 2. So I put a 0 and I carry the 1. Right there. So we add like normal. Now remember, we want to do our discard. And basically, the book talks about how you're subtracting r to the n power. In this case, if you look in the book, it says discard the n carry of 2 to the 7th. Because we originally had 7 digits, didn't we? But it amounts to just dropping its first digit. So 0, 0, 1, 0, 0, 0, 1. And that's our answer. We got one more example, then we're done with that part right there, and we'll be ready for signed binary numbers next time. So let's go ahead and take a look at that last example in the book. Or I guess I could make one up. They're not hard. Assuming you can write them down right. Is anybody still writing that down? Okay. So let me make up one. 1, 1, 0, 1, 1, 1. Got 6 digits, and we're subtracting 0, 1, 1, 0, 0, 0. Let's try that. This is M. This is N. M stays as is. So 1, 1, 0, 1, 1, 1. I'm changing this to plus. What do I do with these zeros here?
We leave them.
Leave them, exactly. Any zeros coming from the right side stay as is. Here's my first digit that's not 0. It's 1, and I told you 1 stays as 1. And what do I do with the rest of the digits?
We flip them.
Flip them. Yeah, so this goes to 0, this goes to 1. And then we want to add this. 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, so I'm going to put a 0 and carry the 1. And remember, we're going to drop this first digit when that M is greater than N. So we end up with 0, 1, 1, how many ones? 5? 3, 4, 5. And that would be our answer. Now maybe I'll split this up into the homework into 2 parts, so you can go ahead and start working on part of it now. Out of the back. This is over on page 37. And let me see, numbers 1.3. 1.4 is interesting. 1.7. 1.8. 1.9. 1.10. 1.14. 1.15. 1.16. 1.17. Let's see, that's 10's complement. We did look at 2's complement also. We didn't really talk about negatives though. But if you have a negative, you just attach negative, so that should be pretty easy. So let me just throw on 1.18 also. So really 1.3, 1.4, and then 1.7. Well, no, there's a few other missing. But that'll be the homework then. Is there any questions on any of that?
Yeah. So that's the problem. So we did the alternative subtraction, but the original one shouldn't have the same answer.
Let me see. Yeah, it should. See, if I do that, 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 0 is 1. I can't subtract this, so I have to go borrow one. This becomes 2, doesn't it? 2 minus 1 is 1. Can't subtract 1 from 0, so I go borrow 1. And then this becomes 2. 2 minus 1 is 1, and 0 minus 0 is 0. So yeah, definitely you can subtract it like normal and check your answer.
I copied it wrong.
It's easy when there's a lot of 1s and 0s. Well, I'll go ahead and stop the recording.